I'm continuing my sequence on domains of functions here. So in this video, I'm going to cover radical functions and combinations of radical functions with other kinds. Now, in a different video, I did polynomial and rational functions, and you can find that if you look for it. And likewise, in a different video, I'm going to do exponential and logarithmic. So this video here covers only radical functions, and then using radical functions as part of a larger function. So let's talk about radical functions. Take a look at the problem set that we're using as an example here. Do you see any radical functions? Well, if you know what you're looking for, you can see that 55 is a radical function, likewise 56, and likewise number 60. Any other functions here that have a radical in them, in this part of the problem set anyway, are hybrids, if you will. In other words, they're a radical function that's combined with some other form. And so that's what we're going to focus on in this video. We're going to show you how to do a problem like 55 or 56 or 62 as an example. Let's take a look at some other examples. So here are a few more examples of radical functions. And you know, it's a lot easier to talk about these if you have some of the vocabulary down. And so give me a couple of seconds here and we'll talk about the vocabulary that's associated with these radical functions. So when you're talking about radical functions, the symbol that looks like a division symbol, the radical, is why these are called radical functions. And for many of these, you'll see a number on the outside, which is properly described as the index. And for a square root, it's not written, but it's understood to be 2. And so you may see other values like 3 or 4 or whatever. And then the argument of that function, the stuff that's inside the radical, is referred to technically as the radicand. And so if you understand these vocabulary words, it makes it so much easier to talk about these types of functions. So once you're able to recognize when you're looking at a radical function, then the next step is to look at what we call the index, because the index is going to tell you quite a bit about what's going on with the domain. So these three examples here, the first two, f of x and g of x, those are square root functions. And so as we were saying, the index is not written, but it's understood to be 2. And so in cases where you have an even index, that would be 2, 4, 6, whatever, in that case, the radicand has to be non-negative in order to keep the function well defined. If you have an odd index, like 3, 5, 7, whatever, then we really don't care so much about whether the radicand is positive or negative, but we may have other concerns, like for example, if we have a hybrid situation where we've combined, let's say, a radical function with something rational. All right. So anyway, let's look at these functions here, and we'll talk about finding the domains. So for this first function, which if I was reading it to you, over the telephone or something, I'd read it as f of x is equal to the square root of quantity x plus 1. So in other words, I'm indicating that the 1 is under the radical with the x. This has an even index, and so that means that we need a non-negative radicand in order for the function to be well defined. So what that means is that we must have the quantity x plus 1 to be greater than or equal to 0, and in order to find the domain, all we have to do is isolate x by subtracting 1 from both sides of the inequality. So if you re-express that little red circle with the arrow is my way of saying I'm subtracting 1 from both sides. That's the same as saying that x has to be greater than or equal to -1. Now if you draw that on a number line, you can see the picture right there, and if you then express it in the usual notation, we would say the domain is x such that x is greater than or equal to -1, or in interval notation, it's the interval from -1 to positive infinity with a square bracket on the -1. So remember, if you have a closed circle on the number line, you're going to have a square bracket on the corresponding value in the interval notation. All right, let's look at the next one. Now the function g of x is a little bit more sophisticated. It may not look like it, but there's actually a little bit more going on here than you might think at first. And so again, you can see that g of x is a square root, and that means we want the radicand to be non-negative. And so we need to figure out, well, how's that going to take place? So what we're saying here is that we need to have the quantity x squared minus 9 non-negative. And there's a couple of different ways to obtain the result for that. We do have graphing calculators in our class, and so that is one way you could get a look at this. It's not the only way, and it's probably not the preferred way, but it's an okay way. And so I'm going to show you on the graphing calculator how you can determine where that function x squared minus 9 is non-negative. Let's take a look at our calculator. So here's my graphing calculator, and you probably are aware that if you want to graph a function using this calculator, you'd key it in up here using the y equals submenu. And it could be that you're renting a calculator, and so possibly somebody who's used it for stats or something has had it before. And so you notice here that plot 1 is lit up, and that means that anytime I put something on the screen, it's going to graph whatever plot 1 is. And so you can turn it off a couple of ways. If you want, you can just go up to plot 1 like that and press enter. And now you'll see that if you move off of it, that it's dark, or that it's not lit, rather. And so it's not going to display. If you have all the plots turned on, which sometimes, it happens like that, you can also do as follows. You can go to the stat plot menu, and you can use command number 4, which is the plots off command, and you just press enter to affirm that, and then that shuts off all the stat plots. So that'll keep your graphs, a little bit cleaner. You won't have to worry about seeing a stat plot from something that you don't care about cluttering your graph. Anyway, let's do the problem that we're looking at here. We wanted to see, where is the quantity x squared minus 9 positive, or non-negative? And so we can key it in. And so you'd key it in like this. And if you want to get a window that contains it, you could just do zoom. And, for most of the functions that we have, number 6 would be okay. Zoom standard. A lot of people will use zoom fit sometimes, and I'm kind of ambivalent about zoom fit because it doesn't always work for every function you might want it to work for. So I prefer to adjust my window size manually, but whatever seems good to you. Anyway, I'm going to go with number 6. And so you can see it gives you a standard window, and it gives you hash marks that are 1 unit apart, and so on. And so that's how the graph of x squared minus 9 looks. And if you wanted to see where it's non-negative, anywhere the graph is above the x-axis, it's going to be positive. And if it's touching the x-axis, it's going to be 0. And so what we're doing is we're looking at the y values. And so you can see that the negative y values, of course, are below the x-axis. And so those are the ones we don't want, or the x values that correspond. Now, in this particular case, if you were to trace this, you can probably see something you already knew. This is sort of a tedious way to do this, and it doesn't always give you the level of control that you want. But you can see that around x is 3, you have the y value being 0. And in fact, if you wanted to verify that directly, you could just go second trace and then put in the value. And so you could put in 3, for example, and you'll see that the y value is 0, which, we kind of knew that, I'm sure. And then likewise on the other side of the y-axis, if you put in negative 3, you get the same thing. And so again, you can see that the y value is 0. And so in other words, you can see that the graph of this particular function goes above the x-axis when x is to the left of negative 3 or to the right of positive 3. And so that's where the function is going to be well defined, and that's what we want to put down. So as you can see, saying that x squared minus 9 is greater than or equal to 0 is the same as saying that we need to have x less than or equal to negative 3 or greater than or equal to 3. And so we can say that domain a couple of ways. We can use interval notation, as you see, or we can use the set builder notation. Either one is fine. Now, I'd be remiss if I didn't mention, if someone were to come to me and say, hey, is that really legit? I mean, if I want to know where a function is a positive or negative, I just throw the graph up on my calculator, and then that's my answer. And, the answer actually is no. There's actually a more rigorous, sort of mathematically correct method of analysis that we would prefer. I mean, there's certainly nothing wrong with using the calculator for sort of an informal discovery, or if you have no idea how to start, you can at least get some guidance from how the graph looks. But especially if you're going up the line to take the business calculus, or what we call survey of calculus course, you'd want to know how to do the more mathematically correct version of that analysis. So let me showcase that. So the proper way that this analysis is supposed to be done is like you see here. You take your function and you're creating something that's called a sign diagram. So in other words, you're looking at the behavior of the components of the function, which in this case is x plus 3 and x minus 3, over different zones of the x-axis. And so you notice that down at the bottom, -3 and +3 are the roots of this function. And so each of the components, x plus 3, x minus 3, is a linear function, and the behavior of that is something well known. And so you can use a test value in each of the zones if you want, or you can just use the overall behavior of the linear function. I prefer to look at it as a linear function. It's a little bit faster that way. And you're supposed to fill out the sign diagram as follows. So let's take the first component, x plus 3. Now that is an increasing linear function, and it crosses the x-axis at -3. It has a 0 there. And so you can look at the graph of x plus 3 on your calculator. That would be y equals x plus 3. Let me showcase real quick here to give you the idea. Here's the calculator, and if you want to graph a second function, all you have to do is go back to the y equals menu. You can turn off the one that we're looking at right now, and then you can put in a second one, which, as we said, would be x plus 3. Excuse me. And so now when we go back to the graph, you can see there's that linear function. And as we said, it crosses the x-axis at -3. You can see the value right here. And so when you're to the left of x equals -3, the function is negative, and when you're to the right, it's positive. In other words, it's above the x-axis. And so you can use your knowledge of the behavior of this linear function, which is pretty well beyond dispute, to fill out the sign diagram. So as we said, when you're to the left of x equals -3, the function x plus 3 is negative. When you're to the right, it's positive. And as far as the other component, x minus 3, that one has a 0 at x equals 3. Again, you can look at the graph if you're inclined to. It crosses the x-axis at 3. So when you're to the left of 3 with this increasing linear function, it's going to be negative. When you're to the right, it's going to be positive. And then as far as the overall product, you know that if you multiply two negatives together, you get a positive. If you have a positive and a negative, that gives you a negative. And if you multiply two positives together, you get a positive. And so we're interested in where the function is positive, and as you can see, that's where the product is going to be positive. And so it would be this zone and this zone. And because we're interested in where it's greater than or equal to 0, we'll take the roots as well. And so as we said, this function is non-negative on the following interval. Now that's the more mathematically rigorous, more widely accepted method of analysis. Again, nothing wrong with using the graphing calculator to help you out a little bit, but this type of analysis is what would be expected later and in other courses besides this one. And actually, this is something that I typically do in intermediate algebra, so it's not supposed to be brand new, but anyway. So that's all well and good, and we'll have a little bit more to showcase regarding this method of analysis down the line when it comes up. But anyway, we have one more example we want to talk about for this particular video here. So regarding the function h of x, which if you notice is a cube root, you can see the index is 3 there. What's the domain of h of x? Well, like we were saying, if the index is odd, which it is here, then we don't really care where the radicand is positive or negative. That's not so much of a concern. So what about the domain of h of x? Well, again, the index is odd, and the argument, the radicand, is a polynomial. And so we know that we don't have to worry about it being unreal or anything like that. That polynomial is going to spit out real numbers for whatever we put in. And so the domain of the domain of h rather is all real numbers, because the index is odd and there's nothing that we can put in as a value of x, which is going to cause this to be undefined or to be misbehaving, as we would say. So let me jot that down. So as far as indicating the domain, if you put it in set builder notation, probably the best way would be, like you see, x such that x is an element of the real numbers. So I use the script r for the reals and the epsilon, which looks like a euro symbol. That notation indicates is a member of, or is an element of, or is in. So that's the way we would say all real numbers in set builder notation. And if you wanted to say it in interval notation, it would be the interval from negative infinity to positive infinity. Now I think actually be remiss if I didn't do as I promised at the beginning of the video, which is look at one of the hybrid examples. So let's take a look. I think a good choice for that would be number 59 that you can see on the screen in front of you here. P of x is the square root of 2 over x minus 1. So you have a lot going on here. You have a radical function on the outside and you have a rational function on the inside. And so we have some different concerns. First of all, we want to make sure that the radicand is non-negative. So in other words, we have to make sure that 2 over x minus 1 is non-negative. And we also have to avoid a denominator 0 where we have x minus 1 there. And so those two conditions are going to have to be satisfied in order for the whole function p of x to be defined. So let's show how we'd write that down. So like I was saying, couple of conditions that have to be satisfied here. First, we have to make sure that the radicand, which is the quantity 2 over x minus 1, is non-negative. And we also want to make sure that the denominator, x minus 1, is non-zero. Now of the two, x minus 1 being non-zero is the easiest to dispose of, because clearly if x minus 1 is non-zero, that means you can't have x being 1. Then we have to think a little bit regarding 2 over x minus 1 being greater than or equal to 0. And so I have a sign diagram down at the bottom as I did previously. And this one's a little bit easier to fill out. 2, the numerator, is a constant. It's always positive. It never changes sign. And so just to make sure that we've accounted for that fact, I'm going to put that in the sign diagram. Now as far as the quantity x minus 1 is concerned, again, you could use a test value if you want, but x minus 1 is a linear function. It has a slope of 1, and so it's increasing. And it has a y-intercept of negative 1, but it crosses the x-axis at positive 1. As you can see, I have the root down there at the bottom. Now I have an open circle on the root because when we take this and put it into an inequality form, even though it's true that the overall inequality was greater than or equal to 0, the denominator roots are not part of the solution set because they make the rational expression undefined. So we have to exclude 1, whatever side we end up taking. Now as far as x minus 1 is concerned, it crosses the x-axis at 1. You can verify this on your calculator or whatever. When you're to the left of 1, it's negative. When you're to the right of 1, it's positive. And so let's put that down on the sign diagram. And as far as the quotient is concerned, you know that if you divide mixed signs, in other words, if you have negative divided by positive or positive divided by negative, that gives you a negative quotient. And so we'll put a minus sign over here. And likewise, if you take the quotient of two positive numbers, you get a positive result. And so we have a positive result on the right side. Now again, because we were looking for where the quantity 2 over x minus 1 is greater than or equal to 0, we're going to take the right side here. And if you take the intersection of the conditions, in other words, x not being 1 and x being greater than 1, it's clear that the intersection is going to be x is greater than 1. And so that's the domain of this function. So this function is defined when x is strictly greater than 1. And that would be the domain for p of x. Hope that's been helpful. If you have any questions, feel free to drop me a line. Otherwise, we have another video for exponentials and log functions.